Mendeleev was completely vindicated in the most dramatic manner possible. Now nobody had any doubts about the table. Well, no serious doubts, but there was still the nagging worry that Mendeleev had needed to ignore the atomic mass order in some cases. The problem was eventually cleared up by the brilliant English scientist Henry Moseley at the beginning of this century. Moseley knew that in certain circumstances, elements could be made to give out X-rays. Moseley realized that the different X-ray frequencies for each element indicated special differences in the inside of the atoms. From this, he was able to give each element a special number called the atomic number. And suddenly, things fitted into place. A smooth increase in atomic number. It's the atomic number that fixes the position of the element, not the atomic mass. Even the tellurium and iodine type problems were solved. They are in the correct position according to their atomic numbers. At last, scientists had a table that worked, and they knew why it worked. And basically, that's still the table we use today.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bits of bromine, lithium, beryllium, and barium. There's holmium, and helium, and hafnium, and erbium, and phosphorus, and francium, and fluorine, and terbium, and manganese, and mercurium, molybdenum, magnesium, dysprosium, and scandium, and cerium, and cesium, and lead, praseodymium, and platinum, plutonium, palladium, promethium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium, and chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
Since that song was recorded in the 1950s, a few more elements have been discovered. Often we use a short form of the table, which looks like this. If the elements are arranged in order of atomic number, some interesting patterns can be picked out. For instance, these elements are all gases at room temperature. This property disappears and reappears at intervals. It seems that these properties aren't just mixed up any old way, there's a pattern. Similar patterns can be seen in the chemical properties of the elements. For instance, these elements are all metals. They conduct electricity. And these are non-metals. They don't conduct electricity. And some elements don't fit easily into either category. Now let's have another look at those elements lithium, sodium, and potassium. The early pioneers knew that they all had similar properties. When the elements are arranged in order, these metals occur at regular intervals. Now that row also contains three other metals called rubidium, cesium, and francium. If the pattern holds good, then they too should react with water in the same way. That was rubidium. Let's see that again. And now cesium. All the metals in this group react in a similar way with water. Mind you, the reactions aren't exactly the same. Remember how lithium at the top of the column reacted with water. But potassium, from the middle of the group, reacted more vigorously. And then there was cesium from near the bottom. These changes in reactivity going down a column are part of a pattern for the whole table. For instance, take the noble gases. There's not much chemistry to see, but there are changes in their physical properties, for instance in their density. The noble gases are xenon, krypton, argon, neon, and helium. A balloon filled with helium rises quickly. A neon-filled balloon rises slowly. An argon balloon falls slowly. Krypton is denser still, and xenon is the densest of all. Interesting patterns also occur moving across the table. For instance, all these elements react with fluorine. This is fluorine and sodium. The reaction's fairly lively. So is the reaction between magnesium and fluorine. And now aluminium powder and fluorine. This is silicon and fluorine. This is phosphorus and fluorine. And this is sulfur. It may not look it, but there is a pattern. A pattern in the formula of the compounds. In the case of sodium, one sodium atom combines with one fluorine atom. For magnesium, one atom combines with 2 of fluorine. For aluminium, it's 1 and 3. And so a pattern emerges. There is a slight problem with chlorine, but then no pattern is perfect. The periodic table is a simple yet powerful way of looking at how the elements behave, looking at their chemistry. For instance, their reactions with oxygen. Magnesium. This is aluminium burning in air. And this is phosphorus. But once more, there's no obvious pattern just from looking at the reactions. But again, there is a pattern in the formula of the compounds produced. The number of atoms of oxygen which combine with one atom of the element changes in a regular way. The periodic table helps chemists make sense of the properties of the elements, and there's an added advantage: they don't have to remember lots of facts about individual elements. The position in the table is an easy way of working out what the chemistry of an element might be. Eventually, all the gaps were filled in. But surprisingly, that's not quite the end of the story. Element 92, uranium, isn't the last. In the 1950s, scientists like Edwin McMillan at the University of California used a nuclear reactor to bombard some uranium atoms with neutrons. The result? A brand new artificial element, number 93, later called neptunium. Elements 94 to 98 were produced in the same way. 1952 saw a momentous happening, the first hydrogen bomb. A giant nuclear reaction, rather like those at the centre of stars where elements were first formed. We've come full circle, so perhaps it wasn't that surprising that elements 99 and 100 were detected in the debris of the bomb. This is modern-day alchemy, one element turning into another with enormous and frightening violence. Today, scientists have reached element number 105. There have also been claims for another 3 elements, but they've not been confirmed. What is certain is that we can predict what their properties will be in advance from their position in the periodic table.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury, molybdenum, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, kryptonium, and radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.